Welcome to MPLAB Harmony for Noobs, my tutorial on how to use this powerful tool from MPLAB. So first thing we want to do is create a Harmony project. File, New Project. We want a PIC 32-bit MPLAB Harmony project. Next, we need to make sure to specify the path that our Harmony files are contained in, which for my instance is in Applications Microchip Harmony version 2.06. We're going to put the project path location, it's just going to be inside the app folder there. This is going to be called tutorial. And we have default configuration, family, the MX family. 360. Dun dun dun. 361. 360 F128, right? PIC 32 MX 360 F512L. Cool. Select that guy. And we are on a custom board, so we don't have any target board to use, and finish. So we're greeted with two pages. The one on the left we configure through, and the one on the right gives us tips on how to configure things, because it's complex tool. We'll go first to our pin diagram. As you can see up here, all gray pins are unavailable for us to use for anything. Blue pins are things that we can assign, and green pins are things that we have assigned. So then we can assign pins by going to pin settings. So if we look at our schematic here, we're going to be grabbing UART2, so that's pin 4950. 49, we want to be UART2RX, and pin 50 here is UART2TX. We automatically fill in the names there. Let's grab some LEDs. Looks like they're all on port D. So we'll come in and sort this by ports. Port D, pin 0, is going to be an LED with an active high state. I'm curious if I hit active low. No, it doesn't do anything different. But we can change the loading state here. So if you say high, the LED will come online, or we can say low and it will stay offline. And we can come in here and rename it to LED 0 by double clicking and then enter. And then we'll call one more LED out here, LED 1, enter. What else do we want? Let's grab these analog inputs here, so that's pins 25. Go back to pins 25 right here, analog input 0, and pin 24, analog input 1. And I believe that's all the pins we're going to use for this tutorial. So if you look at our pin diagram, we can see everything that we have used, and now it is labeled for us, which is pretty nice. So after I've got all my pins assigned, I go into my clock diagram here. So let's stretch this a little bit so we can see the whole thing. So we have an 8 megahertz crystal in. We are going to be with 8 megahertz in. We want to get 48 out here for the USB. Is set to on. The USB circuit is driven. Proper operation needs to be. So we turn this guy on. We want to turn this guy on. And what are you saying now? Is driven by FRC. Okay, we want a divide by 4. I don't think this message is updating. But if we come in here and we say we want to drive with 16 megahertz is our output. Now it updates and says that everything is still wrong. For accurate operation needs to be 4. So we used 2 here. And then in order to get it to update, we have to update this field for whatever reason. So now we got 4 megahertz here. You're happy. What if we switch these guys back to off? Hey, look, the clock is happy now. So you need 4 megahertz at this point from whatever your oscillator is. And then these guys need to both be switched off. Cool. Speaking of that, I forgot to come over here and change this to high speed to make sure that everything goes fine. The frequency needs to be between, oh, okay, apparently I need to use the slower one. Oh, that's nice that they do that. Okay. We've already taken care of this with auto calculate, so we have 16 megahertz out here. We're not going to do a post cal to my peripherals, and we don't care about any of this other clock stuff. But as you can see, it's pretty easy to set up, especially with that auto calculate button that lets you cheat pretty hard. Okay, next up is our options. For this tutorial, we are going to be using most projects start inside of the Harmony framework configuration under drivers. So we are going to set up our UART first. So we want to use the UART driver. We have the option here of a dynamic or a static implementation. Dynamic is good if you're using multiples, like 9 UARTs, or even if you're just using 2 UARTs. It's good because you can move pointers around and save code. But for our application, we only have 1 UART port, so we'll statically enable this. We want interrupt mode, we want byte model support, we want callback operation, not blocking operation, because blocking is dumb. Number of UART drivers, 1. We are going to be UART ID, we are using number 2. Baud rate of 19200. Interrupt priority, 4. Level 7 is the highest, nothing can interrupt a level 7 interrupt. Sub priority, don't really care. Operation mode, don't care. Wake up start, don't care, don't care, don't care. 8 bits, no parity. 1 stop bit, yep, that's good. Handshake, no handshaking. Yep, just the RX and TX lines. So that's our UART driver. We'll scroll up a little bit here and we want to enable a timer. We're going to use the timer driver. We're going to use a static instance because it makes life so much easier. We want interrupt mode, 1 timer, timer module 1, interrupt level, we'll put it at a level 5, sure. Don't need the alarm. We're going to have a prescaler of 256. So I have my fancy calculator back here. So I can say we want 50 hertz. We want 16. Our clock FRC is 16 megahertz. We have an input divider of 256. So in order to do this, we need a PR value of 1250. Timer period, 1250. So that should give us an interrupt every 20 milliseconds. Okay, that timer is set up. Next thing, ADCs. Use the driver. Static by default. Mode. We want interrupt mode. Priority level 3. We'll make it 5. Sure. Clock options. We're going to leave those alone. Sampling options. Enable auto sample. Yes. This usually works out fine. Enable sample scanning. Scanning is great because you can say grab analog inputs 1, 2, 4, 8, and 3 and then tell me when you've collected all of them. It's fantastic. Conversion options. Yep, that looks fine. Right, ADC internal count. Yep. result format 16-bit integer. That'll put everything to the right. Unsigned, right? Yep. Result, buffer result mode is one 16-bit word to 8-bit words. Oh, we want all 10 bits of resolution on this ADC, so we'll keep it in 16. Other options. Don't care. That's kind of cool, actually. I didn't notice this one before. Whatever. Negative input. Yep, don't care. Number of analog inputs, 2. Cool. So this is a scan channel. We're going to use analog input 0. And this one is going to be another scan channel. And it's analog input 1. Yeah. Hush your face. Alright, that is all of our configuration. So if you come over here and look in source files right now, there's nothing. We'll hit save over here. Then we'll generate some code. I like to make sure to turn this guy off so I don't just fill my hard drive up full of all kinds of useless files. And then if any changes, which we won't see any because this is our first build, it'll tell us to merge. And we'll come back to that one later. So generate. Here we go. Closes itself automatically. Then we can come over here and we see that we have a bunch of files now. So framework contains one file, and that is the configuration or the system basic functions such as disabling interrupts and enabling interrupts in here. Pretty good stuff if you're dealing with interrupts. Then we can come into system config, default, framework, and this is where all of our drivers that we built are generated. So here we have like our ADC and our timer and our UART drivers. Alright, all C projects start in the main.c file. So let's open up that guy and see what's going on. Got a pretty basic main here. We initialize the system and then we just run system tasks all the time. The easiest way to find things in MPLAB is to do a command or control click like this, and it'll take you to its definition. So our system tasks, its only thing it does is app task. So we click app task. We're now in our app.c file, and we can see that we go through a state machine. So we have our initialized state, and then after we've initialized, we come into our service tasks, and you can add more states in here if you need a more complicated machine, but for most applications these 2 states is just fine. So all of our initialization that we need to do goes here, and then our main runtime program goes there. So let's get some things initialized here. So we want to initialize our ADC. We open up our ADC driver. We see there is a driver ADC initialize. We'll copy you, paste. Let's put in a comment, ADCs. Alright, what else do we got in here? We also have a deinitialize, don't care, open. We'll need that one in a little bit. Close, start. Add channels. This is the one that we want because we're using scan mode. So we'll copy you. We want to scan add. And if we jump back to the definition, we see that there's this special type that it's looking for, a div ADC analog input. So if we select him, we're taken to what looks like an enum, that has our different channels that we've named. So because of this, say that I had put these guys backwards, it would then call analog input 1, 0. And so it allows you to rearrange things nicely. But we did everything straight today. So we can copy you, paste, and then it looked like the other one just added a 1 on, so we'll copy this line, put more enters in there, paste. Analog input. So now we've added both of these to our scanning, and we can come back to our driver here, and we want to open our ADC, and then the last thing was to start our sampling. Then from there, everything will be interrupt based. Next thing up, we want to do our timer. So if we jump into our timer, we see there's two different files. We have a mapping file, which is essentially the dynamic driver that you can use if you would like, but we have a static implementation that just goes through and calls everything for us with a reference to timer ID 0. So initialize just passes in our timer ID 1 on everything for us, which is pretty nice. So we want to come in here and say initialize, and then if we jump back there, we have a resume, a start, a suspend, a stop, and a bunch of status, and clear, count frequency. Oh, that's interesting. Blah, 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 blah. We don't really care. We only care about this start method here. Okay, so before we go into UART, I'm going to show you how to finish setting up the interrupts for this guy. So we are going to come up here and make a target location for them. We're going to say void ADC event. It's a void. And we're going to also make a void timer 1 tick event. Here a void as well. So then we have these two places that we want our interrupts to go to. So then we can come down and we have these different files here. So we want system interrupt, and we see that we have a UART interrupt vector up here, and we have a ADC interrupt vector and a timer 1 interrupt vector. So for our timer 1 and ADC, we want to come in and add a callback to our app, which was ADC event and timer 1 tick event. Let's make sure I built those right. Yep, that one worked. We can hit back. And this one worked as well. Sweet. Cool. Yep, so that makes it really easy to set up your ADC, or that makes it easy to set up your events when there's only one interrupt vector. Our UART is a little bit different though, so that is why I'm doing him last and separately. So if we dive into our UART, we have our mapping file, which is our dynamic driver. Paste U, jump back, and then we have a deinitialize. We can grab some status, task transmit, task received, task error. Open. We won't worry about you because I know you're implemented better somewhere else. And most of these functions we are not going to use, but you could if you wanted to. I just wanted to show them to you. Most of the UART stuff ends up in this driver UART static byte model.c file that we want to use, like our read and our write, check our buffer size, buffer empty, transmit buffer is full, and primarily we need to set up our callbacks. So we can copy our transmit callback. Let's close a few of these files, we have too many open now. Don't need you. So we initialize, and then we want to set up our callback. And if we go back here, we can see that it is looking for a special driver UART byte event handler. So if we click U, we get a type void. And this one took me a little while to figure out, but essentially we want to copy this guy here and go back to our app, and we need to create an event, void transmit event. And instead of having a void return, we need to have that thing in there. And we'll also make a void receive. Oh, that's right. With the same argument. Boom. Okay, so then down here, to set up our callback, we want the address of our transmit event. So we say transmit event with an and for address. Then we can jump back here and grab our receive event as well. Paste address of receive event and close. Then we also want to say at this point enable transmit interrupts. So if we come into here, we don't get any tools for enabling transmit interrupts, but if we come back to our static file, we have task error, close. Yep, we don't care about opening. Task UART bot set. So if we see here, nope, not there. Here, they use this source status clear, interrupt source enable. Copy you, come back here. Actually, I wanted that whole line. Copy. I need to just close this file, I just keep coming back here. Okay. And paste. And we can jump in on this receive guy, and we can see right next to receive there's also transmit. So we'll copy you. We want to enable transmit interrupts. Cool. That finishes our setups. Now let's get this program to actually do something. So inside of our ADC event, we're going to capture our results. So we'll have an int ADC val is equal to 0x0000000, and then to read our, so at this point all of our ADCs have been converted, so then we can read them. So if we come back into our ADC static class here, we have a read sample. So we can copy U and we'll say ADC val is equal to read sample from channel 0, close. Nice. Let's set up so that whenever we receive something, we'll echo it back. So if we come back into our byte model, we have a write byte and a read byte. So every time we, oh, nope, don't change the code, copy U. So every time we get here, oh, too much. We want to write back whatever we read. Read. So we get an event that we've received something, we read it out of the buffer, we write it back. Close. Cool. Let's go with that for now to verify that our receiving and transmitting is working. So come in and program our device. Let's turn on my Picket 3. And while we're waiting for that guy to initialize, we get serial tools, my terminal program launched. Looks like we're good here. We got our analog port, we're at 9200. We're going to turn Leco Echo off. Let's leave it up. Pick, yep. Boom. Okay. So now if we jump into a terminal here and we hit connect, we should see that whenever I type, I get an echo back. Hello world. Turn off echoing. Sweet. Okay. Having a program that just echoes is cool and all, but let's make this actually do something. So let's come in here, and every time, we'll say that every time the timer takes, we want to send ADC value as a string. So we need to make a two-string method. So we'll have some int string, we'll call this decimal number is equal to 0, and we'll have some int temp value is equal to ADC val. Wow, temp value is greater than 1000. Decimal number plus equal 1. Temp value minus 1 minus equal 1000. So we take care of our thousands, and then we want to say write decimal number ORed with 0x30 to convert it to a string. And then after we have done that, we need to set decimal number back to 0 and do it all over again with our hundreds. Copy paste for life. Oops. And then at the very end, we will send a new line character. Now I can get away with rapid firing these writes because I know that my UART buffer on this pick is 8 levels deep, and I'm only loading it up every 20 milliseconds, so I don't need to worry about overrun in this situation. If you were worried about overrun though, you can come back in here and check is your transmit buffer full, and then handle that accordingly. Okay, let's program this guy and make sure it works. Program. Jump back over here. Yeah, look at that. And then we can move around our joystick and we can see all the different numbers. Sweet. So now I'll show you how to change a configuration after you've built it. So I noticed when we were back in our system configuration or interrupts that this guy was at the wrong interrupt level because he was matching with our ADC, which is at level 5 as well. So we want to change our timer to be a level 3 interrupt, and we'll save. We'll generate the code. It'll ask, do you want to save? Yep. Same thing here, but we'll notice that when it's all finished, it's yelling at us saying, hey, you changed one of my files. How do you want it to handle this? So the X here will delete anything on the right side that doesn't exist on the left. The blue arrow will take anything from the left side and implement it on the right. And whatever is on the right in the end is what will be used. So we want to take this change and leave everything else alone. And we want to close, and it will complete its merge. And we are good to go again. So that is my little tutorial into how to use the MPLAB Harmony drivers to make code development go so much faster and be more reusable. And I hope that it's helpful. Please leave me a comment if you have any questions. I'm pretty new at this stuff as well, so we might be learning together, but that's not such a bad thing. Until next time, peace.